Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, so I think we're going to get started. Welcome to the session on specialized computing in the cloud. We have an excellent set of speakers and a really exciting agenda ahead of us. For those of you who are not up to date on what's been going on in the field of computer architecture, there's been a major disruption brought upon by the slowing and the ending of Moore's law. And some in the community have been looking at specialization as a way to continue to bring forth improved performance and energy efficiency. So you're going to hear multiple talks today that touch on different applications and approaches to specialization. So each talk is going to be about 20 minutes long. We're going to leave 5 minutes in for Q&A, so please hold your questions till then. And hopefully we'll have enough time at the end to have more of an open discussion. So let me introduce our first speaker, who is Martha Kim. So Martha is an assistant professor of CS at Columbia, where she leads the arcade lab. Martha's research interests are in computer architecture, parallel programming compilers, and low-power computing. She's explored low-cost chip manufacturing systems, reconfigurable communication networks, and fine-grained parallel application profiling techniques. She currently works on hardware and software techniques to improve the usability of hardware accelerators as well as data-centric accelerator design. Martha holds a PhD from University of Washington. Welcome back.
Thank you.
And a BS in CS from Harvard. She's a recipient of the 2013 Rodriguez Family Award and a 2013 NSF Career Award.
Thank you, Eric. Okay, I think I just need to, and 3, thanks. Play from start. Perfect. Okay, so thank you all for coming. As Eric mentioned, this afternoon I'll be presenting some of my research group's experience in developing a specialized hardware accelerator. And in our case, the domain that we were targeting was large-scale data analytics. And since this is not necessarily a hardware crowd, which is usually who I find myself speaking about these things to, I thought, and also I'm the first presenter in this session on accelerators, I thought I'd take a few moments at the start and just briefly outline some of the kind of issues surrounding specialization, because these changes that we are considering making at the low level in the hardware can very, very quickly propagate up the stack in ways you may not like. Okay.
Sorry, we need to drop the resolution.
No worries. I just resume.
Yep. Sorry.
No, I was right on the first slide. Excellent. Okay. Right. So as I wanted to say, I want to do a little quick background and primer on kind of the issues surrounding specialization. So there are really 2 questions that one needs to consider. The first question is, why should I even consider specializing? And the answers are right here on these axes, which is for power reasons and for performance reasons. And if you can see from the labels that I've just put on these axes, we're not talking about marginal benefits. We're talking about orders of magnitude. The specific numbers will depend on what exactly you do and what application you're targeting. But at one end of the spectrum in the upper left, you can take, for hardware-wise, a general purpose processor and program it to implement your function X. At the other end of the spectrum, you could build yourself a full custom ASIC, which is an application-specific integrated circuit that has been manually laid out by VLSI engineers. And this circuit does nothing but X really well, really efficiently. But you can't really use it for anything else. And in between, as you can see from where I've placed them on the plot, there are enormous differences in terms of the efficiency and performance characteristics you'll find with these 2 implementations. And in between, kind of spanning that gap, there are other options. So for example, in the third talk, you'll hear from Adrian, who's going to present some work that Microsoft has done with FPGAs. FPGAs are here in the middle of the plot. And these are kind of, FPGAs offer you a midpoint. They are programmable hardware devices, but you're programming them with a circuit to do X. So they fall somewhere between the spectrum. And again, the numbers I've labeled here are derived from the literature, and I'm giving ranges because it depends on how you design your accelerator and what sort of workload you're targeting. The specific benefits you'll see. Okay, so this is why one might consider doing it. If we live up in software in the upper left where it's blue, and we start to care about power or performance, it's awfully tempting to wander our way down to the lower right. Okay, so the second question is, of course, why should I not do this? And because we're specifically focused on the data center in this session, I'm going to kind of outline these issues as they apply to data centers. But really, any accelerator in any device of any size would encounter these sorts of things. So on the left-hand side, I've depicted a rack of homogeneous CPUs. And if you're the guy responsible for maintaining a data center or designing it, this uniformity is extremely beneficial. You can quickly swap in and out parts, and if the CPU on the top stops working, no problem, I'll send the load to the bottom. By contrast, if you instead have a rack where maybe at the top you've got a few CPUs, but then you've got all sorts of other widgets to compute X, Y, Z, and W, while your accelerators, and suddenly your only W accelerator stops working, you're kind of in a lurch. So the heterogeneity there poses very real and very practical problems from the perspective of designing and maintaining a data center. Even just regularity and form factor is a real issue. From the perspective of programming one of these racks, we all know parallel programming is hard, but at least it's uniform parallel resources. In contrast, if you're trying to program this guy on the right, well, you might have different APIs, different ways of invoking the different accelerators. What if some other app is running and it wants the accelerator, so you might not be able to get at it? This is for sure more arcane, more complicated than what you'll find in a uniform situation on the left. And then finally, as far as what you can actually compute, on the left-hand side, if the workload changes, no problem. Update your software, run different software, no harm, no foul as far as the hardware is concerned. But here, you've now baked into silicon the things you're trying to compute, the functions. And so if you change your mind and say you no longer wish to compute W, but you've invested in a W, space in your rack, designer time, engineer time, you can no longer use this thing. It's just, a doorstop to you. So there are very real challenges. And personally, as an architect, our community is very comfortable and very accustomed to focusing on things like power and performance. We can measure them, we can improve them, and so these are games we play well. And frankly, these reasons are the things we really struggle with. How do we can build good accelerators, but how do we make them readily usable, practical, and kind of practical both in a programmatic sense and also a business sense? So these are the big issues surrounding this question of specialization. Okay, so in the context of this tension, I've broken my talk into 3 big sections. In the first section, I'm going to tell you about a data analytics accelerator that we've designed. This is my lab back at Columbia, primarily the PhD students there. It's called the Q100. It's a data processing unit. So kind of like a GPU, this is a DPU. In the second section, I'm going to tell you about, having designed the first one, we now have much better ideas about what the second one should look like, and so I'd like to impart some of those experiences. And then finally, in the third section, I'll briefly highlight some of the challenges that we see with respect to system integration, both integrating this new device under software and integrating it in with the hardware. And so I'll briefly touch on those at the end. Okay, so here are kind of the 4 top-level headlines about the Q100, which is the name of our database processing unit. The key design feature, and this is a big aspect of my initial architectural motivation here, is that this is a processor that is designed to process streams of data. So we're going to interact with memory not in terms of raw loads and stores, but in terms of bring me in that column, write out this column. And so these streams represent columns or tables that you would find in a relational database. We're specifically targeting analytical queries. This is essentially one half of the database world. You have a big pile of data. How do we comb through it and analyze it and extract useful information? There's a whole second half, which involves updates and transactions. When I buy a pair of shoes at Zappos, they record that transaction. That's not the sort of workload that this chip targets. You'll find that we have directly implemented in hardware several kind of common relational operators. And then the ISA, the instruction set, is both spatial and temporal. All this means is that a temporal ISA tells you over time, do step 1, then step 2, then step 3. And a spatial one tells you do step 1 here, step 2 here, and step 3 here. And those are all independent, but spatially parallelized. Okay, so working from the top down, here's just a flyover of how this device works. So say you have some query, and I'm showing one here in SQL that, what's it doing? It's computing a quarterly sales report for the total sales. So the query at the top there can now be boiled down into an execution plan that we're expressing here as a graph. And in this plan, the nodes in the graph represent operations, such as an aggregate or a column select, and the edges between them represent dependencies. And these edges have data streaming along them. So it's not a byte or a word or a struct, it's a column from a table. And as far as constructing this plan, you can do it either manually or compile down. We've done both, and our manual plans are a little better than the compiler output, but they're okay. And if your intuition is that this is an important step, you're actually absolutely right. This planning stage is a big determinant of your quality of result. Okay, so then given a plan, we need to map it to a particular Q100 device. And so the hardware itself, which I've depicted here on the right, it contains some finite set of resources. So kind of surrounding that interconnect up there, you'll see there are 2 diamonds and 3 trapezoids and whatnot. And that depicts, I have 2 of the diamond tiles and 3 of the circles and whatnot. And my plan may require more tiles than I have. And so what we're going to do is we're going to schedule the plan onto the available resources. This is a fairly standard scheduling problem where given a fixed set of resources and respecting the dependencies in the plan, we're going to say, all right, given what I have, I can do that whole blue chunk of work first. Then in the next time step, I can take the next chunk. And then finally, it's going to take me 1/3 step to complete the rest of my plan. So this is a simple temporal scheduling operation. And then the last step is to go execute this plan. So the inputs reside in memory. We stream in the initial data and bring it into the first operator. And I haven't depicted it here simply because the figure would be a mess. But these operators, to the extent there are dependencies between them, that data streams directly point to point on chip. And eventually, once the blue work is done, there's some edge in that plan that was cut between the blue and the red, the next step. That result needs to be spilled back out to memory. And then we just repeat this process step by step. So we suck that result back in, compute it in the red stage, and spill it again, and then the 3rd step happens. And so essentially, you read from memory, compute, and spill until you have completed your query plan with the available resources. And so immediately here, there's this trade-off that you can see that the more resources I put down, the fewer spills I will incur. And this is part of the design space that we've explored. Okay, so I want to be a little more concrete about these tiles because this turns out to be important when I go to explain what we want to do next. So bear with me. It's going to be, at the risk of giving you too much detail, I feel I need to share this. So I'm going to start with a very, very simple tile, and then I'll show you the one that really matters. So this is our simplest tile. It's called the Boolean generator. It's just a comparator. And all it does is take in 2 streams of data, here in 0 and in 1. And in a relational system, these things correspond. It will do some comparison as dictated by the configuration information up at the top. And then it will spit out just essentially 1 bit per comparison result. Say, that one failed, that one passed, that one failed, that one passed. So tiny little bit of analysis. And then based on that predicate, you might, And in fact, almost always we take this Boolean predicate and use it in conjunction with a second tile, such as a column filter, where using that predicate and some other data, it might be a third column, it might be one of the same, match them up, and selectively output those for which the comparison succeeded. So this is your basic where clause in SQL. You can string together a bunch of bool gens and do this filtering. Okay, so that's a pretty simple tile to wrap your head around. There are more complicated ones. So I want to introduce a tile that performs the range partitioning operation. So for those who aren't familiar, range partitioning, or actually just partitioning in general, is a pretty common operation in databases where you take a big table, and because it's so big, it or its associated metadata just won't fit in cache. So in order to process it more efficiently, what you do is first partition it into smaller tables and then process each of those partitions in parallel or even in series, but with better cache locality. So range partitioning is a specific flavor of partitioning where we're going to partition the key space or the domain of keys into particular ranges. So if that's my big input table on the left there, I have a number of splitter values, which here I've just, for the example, said 10, 20, and 30, and those are my cut points. And then what I want to do is break the big table into smaller tables based on the values of the keys and how they correspond to the splitters. Okay, so that's what we want to compute. I'm now going to show you the tile that does this. Okay, so using kind of the visual language of the previous tile, I have coming in on the left my input table. So you can think of it as a key column plus some other data, basically payload that I want to keep associated with the key. And what I want to have coming out here on the bottom are each of my output partitions. And kind of configured in at the top are the splitter values. And again, I'm depicting 3, but these are typically much higher fan-out partitions. So if you were to look inside this tile, you'd see a circuit sort of like this. If you kind of squint at it and pick out these registers, you're going to find that it operates in a pipeline. So I have a little example. I think it's the same one. So my splitter values get stuck in registers that I've shown up at the top there, 10, 20, and 30. And then say I have a record with the key value 15 that comes in. I'm not differentiating key from payload because they kind of just travel in lockstep anyway. So 15 comes in, it'll be compared with 10. It's not smaller than 10, and so it will just advance in the pipeline. It is smaller than 20. And so at this point, this kind of smaller than condition will be found to be true, and this record will be kind of dropped out of the conveyor belt at the appropriate partition. And so just think of like a pachinko machine with things rolling along and falling out as appropriate. Okay, so this is how this tile operates. And we have, I'm showing you this because I would like to refer back to it in a little bit. Okay, so we have 11 such tiles. So I showed you the bool gen and I showed you the partitioner. And here what I'm plotting is if you were to inspect the circuit for each of those tiles, so each of these functions, you'd find that they vary. Of course, they all do different things. So here we see that they all have different critical paths. But this resource imbalance is really problematic. What it tells us is that that my partitioner is setting my critical path, and that column filter guy that I showed you earlier, he's got 80% of the clock cycle where he's just idle. He's not doing any useful work. So I have a slight imbalance in terms of how I'm using, at a very, very fine grain, the clock cycles. This is another thing we're going to come back and fix in version 2. And if I were to look at the area and power consumption of the tiles, I'd see similar sorts of issues where some are big and some are small. And having dedicated, say, a large chunk of area to my partitioner, if I have a query that doesn't require partitioning, there's nothing I can do with this current design to recover those resources. I've spent them on partitioning. If I don't happen to need partitioning, I just can't get any value from them. Okay, so to quickly kind of close the loop on the Q100, I'm happy to discuss the designs and the issues surrounding this thing much more offline. In order to kind of compose an entire accelerator, you introduce some mix of these tiles. And so we looked at a design space. You wire them together, and then you kind of see how fast queries you care about run. So in this case, I've plotted here runtime versus power of a common analytic benchmark suite. And you can see, there are trade-offs to be had. And so picking 3 out, kind of the lowest power design, the highest performance design, and some kind of more balanced design on the Pareto frontier, we can take those 3 specific designs and compare them to actual software. And just briefly, here's kind of relative energy, relative power, relative runtime. This is relative to the same software running on MongoDB. It's an open source column-oriented DBMS. It compares favorably. And another kind of nice experiment that we did that I found interesting was that if you say, hey, I designed this chip with one particular data size in mind, and then I made the data 100 times bigger and tried to shove 100 times the data through the chip of the original size, what happens? We see that we do take a hit on the runtime. This is the same circuitry trying to churn through 100 times the data volume. It's going to take longer. However, the relative power and energy still hold up pretty well, which we thought was a promising effect. Okay, so I started the presentation talking about the whys and why nots of accelerators, and hinting at this notion of there are kind of good and bad ways to go about doing this. So I want to highlight a few of the things that we would do differently next time. So briefly, these 11 tiles that I've just summarized, they're all unitaskers. Yet if you actually look at the circuitry under the covers, there's a lot of commonality amongst them. And so this is what we would like to exploit to have a more generic notion of resource that we can better shape to our queries. So let me explain exactly what I mean. So here's that partitioner again. What I had was stationary red data, my splitter values I put in at the top, and then I had this stream of blue data that marches along and is alternately at each stage, the blue record either advances or falls out based on the output of some comparison. So if you think about a different operation, for example, a merge, where you have 2 ordered streams and you want to merge them, again, in order. I'm still showing the HARP circuitry, but I've kind of scribbled colored lines over it. Think of it as a red and a blue stream. They're both advancing, and based on the comparisons, one advances and one holds. And so they'll alternately block until you get, from the 2 input streams, which now move, a single merged output stream. And in this scenario, we're not using any of the vertical options. But again, you have the same sorts of things, comparing corresponding elements and then conditionally advancing based on the result of that comparison. And you're also doing a little routing. In this case, we're going straight. With the partitioner, we had the option of turning right to go downwards. And you can even kind of keep doing this to more complicated operations. So just to throw out, one that was fairly new to me as a non-database person, there's this thing called a nested block loop join, where you essentially want to do an all-to-all comparison amongst 2 tables. And you can even do that with actually very, very similar hardware, where to compare all red records to all blue records, you stream in a chunk of the red table, as many as can fit in your available hardware. Then you stream by the entire blue table, and whenever the join condition matches, you bring down here the combination. And then again, you need to stream in the next step, the next chunk of the red table, and you repeat this process until all records in red have been compared using the filter to all records in blue. Okay, so those are just 3 quick sketches of how these sorts of resources can be kind of programmatically combined to execute analytic operations. So for GPU 2.0, we would do something that looks more like this. We'd say, hey, look, take each of those pipeline stages as its own homogeneous programmable tile and array them not only in horizontal pipelines, but vertical columns. And then what we've really done is mashed together the storage of those buffers, which I've depicted as red and blue, the routing options, which again is conditionally based on various protocols and data comparisons, and then of course some combinational logic for those comparisons, which I haven't even drawn in this picture. And so what you find is that we have now homogeneous resources. So I'm hoping this will yield better resource usage. If I have a join-heavy query that requires no merging, I don't have to program any of these guys to do the merge protocol. Whereas if I have the inverse, I can handle that as well with the same resources. So we're hoping to see better utilization. Similarly, the interconnect here, I didn't highlight this with the old design, but this is a very regular point-to-point interconnect. So we've got lots of little short local wires where the routing is kind of spread throughout these little programming protocols. And then, I already mentioned the unification of the buffering and the routing. Okay, so because I can see I'm running low on time, I'm just going to tell you the two things that I was going to tell you. And if anyone would like to discuss this further offline, I'll stick around. So I wanted to highlight a few of the issues surrounding integrating an accelerator into a general purpose system. Because really, the things we do low level at the hardware can very quickly become, some or many programmers' problems. The way we integrate the accelerator with the CPU determines the dispatch method, which determines how long it takes to send a chunk of work over to the accelerator, which in turn determines how much work, how big chunks, how small chunk you can afford to send over there. And so very quickly, this affects much, much higher level design decisions. So there are two things that we think are promising, and I'm just going to tell you what they are. So the first relates to this data-oriented analytics, which is, we found it very beneficial to exploit existing software interfaces, higher level interfaces. So in this case, in the database world, there are DBMSs, and there is SQL. So there is a standard language, and there are certain tools, software runtime systems, that can help hide these potentially unwelcome hardware changes. So this is a picture of our compiler, which I won't go into. And then the second is in the realm of unifying accelerators and CPUs in a single address space. This just makes programming easier. You don't have to marshal data on and off. But you need to introduce some hardware to do that. And we've done some experiments that indicate that if you naively introduce address translation hardware into an accelerator, you're going to give up all your performance benefits. So this can be done, but there are, again, right and wrong ways to do it. But we think this is an important thing to kind of facilitate the adoption of hardware accelerators. So with that, I will close and just return to the summary slide, and I'll take any questions. Do I have time?
Yep. So let's thank our speaker first. So we have time for maybe one or two questions while our next speaker gets set up. Oh, and please wait until the mic gets to you. Yep. It's on its way.
I'm just curious, does your sort tile use the partition tile?
Yes, that's part of the reason that we actually chose to implement the range partitioning flavor of partitioning.
Okay.
Is that the sort, I wouldn't say it uses the partition tile, but it certainly depends on it. So if you have, you need to sort a large body of data that's larger, say, than what can fit in the sort tile's buffers, you need to, in this initial design, partition down until it can fit.
No,
and range partitioning has these
The follow-up question is, how come your sort takes a smaller amount of time than your partitioning tile?
The charts I showed? That's not execution time, that's critical path length. So it's more a property of the circuit than the operator.
So I think we should probably move on to the next speaker, but if you have more questions, please talk to Martha offline. Let's thank her again. So our next speaker is Tom Wenisch. He's an associate professor of CSC, University of Michigan, specializing in computer architecture. His prior research includes memory streaming for commercial server applications, store weight-free multiprocessor memory systems, memory disaggregation, and rigorous sampling-based performance evaluation methodologies. Tom is currently looking at computational sprinting, data center architecture, energy-efficient server design, and multi-core multiprocessor memory systems. Tom received the NSF Career Award in 2009 and previously was a software developer at the American Power Conversion, where he worked on data center thermal topology estimation. He holds a PhD from Carnegie Mellon University.
Thanks, Eric. Thanks, everybody, for coming. So I'm going to tell you guys about thin servers with smart pipes, which is sort of my first foray, along with my students and a whole bunch of collaborators, to think about how we can use sort of accelerators and SoC technology in this sort of wonderful landscape of trying to integrate different pieces to improve energy efficiency in the data center. So the interesting anecdote about this particular piece of work is you can see from the set of co-authors that we have a pretty diverse set of companies involved on this particular paper. So shortly after we published this, a bunch of reporters called looking for a conspiracy theory. Why were all these companies in bed together? Sadly, there is no conspiracy. It's just sort of the happenstance of where people have moved around. So the sort of taking off point for this line of work is that there'd been repeated efforts over the last few years to try to implement data center applications with more energy efficient processors of the kind that we'd have in sort of our cell phones and embedded systems. So, let's take something like an ARM core, maybe something more powerful than an ARM core that has less stuff but is more energy efficient, or at least draws less power than the big beefy, big iron cores that we put in servers. And so it's been pretty hard to do this because it's been pretty hard to get good enough performance. And sort of the question is, if we can find a lot of what those processors are spending their time executing and offload that to some bit of hardware on the side, maybe the work that's left over that's more complicated, that would be very difficult to cast in hardware, can be executed on one of these much more lower power cores that we can then integrate at much greater density and so on. And sort of the second taking off point for this project is that when you think about sort of data center applications, which are large distributed systems where these different clients and servers are sort of talking to each other over the network, Memcached is about as simple as it gets. Right? This thing is pretty dumb. It doesn't do anything. It does a key value lookup and returns one packet over the network in response to a request. There's no coordination. If we can't do it here, we're certainly not going to be able to accelerate many other kinds of very complicated distributed stores. And so it was nice because there's really just 10,000 lines of code. How hard can it be? So with that, let me step back and give just a little bit more introduction to why would this be an important thing to think about? And key value caching layers, not necessarily Memcached, but other kinds of key value caching layers, really are pervasive in large-scale internet services. So Memcached is one particular open source piece of software that we know at least Facebook uses some variant of internally, and it really is key to them being able to scale to the amount of traffic that they support. So it's really critical for these workloads where you want to get interactive access to data with low latency and very high throughput. And one of the nice aspects of very simple key value stores is that if your number of customers grows because you have a great idea and your web service is taking off, and sort of you have to start caching more data, you can organically scale up the size of the cache to keep up with the amount of data that's being stored. And through some simple tricks like consistent hashing and so on, you can make it relatively easy to manage and increase the size of a software pool, a cache pool. Now, because these things have grown organically over time, there's also sort of been incremental software refinement really targeting the kind of commodity servers, sort of general purpose, high-end servers that run all sorts of things in these data centers. And so there might be some opportunities on the table to sort of rethink and do things completely differently than we've arrived at just through this incremental refinement. Another key aspect of this kind of workload is that we actually care quite a bit about the performance of an individual server, because since any client may end up talking to any one of these Memcached servers that happens to be responsible for a particular key value pair, that one server, if it becomes busy, could become the bottleneck, right? Or it could be the thing that limits the overall performance of my web service. And at the same time, because I don't want to, ultimately I'm limited by the power capacity of my data center, I would like it to be power efficient. That is, I want this to be quite good from a peak power perspective as I grow these pools. And so the question that we were really posing is this approach of kind of the current latest optimized variant of the open source software running on a commodity server efficient? And how do things compare when I consider the sort of big iron best thing that Intel will sell me to something that's a much more modest but perhaps more power efficient server, peak power efficient server, something like an Intel Atom class processor? Okay. And So the first step in trying to figure out what should this accelerator do is we took a look at what does this workload look like when you run it on these sort of two ends of the processor spectrum. And what we discovered is that neither of these things was actually particularly good if we're trying to optimize the efficiency of a key value cache. So surprisingly, perhaps, despite the simplicity of the workload, the execution time of this is dominated by lots and lots of stuff that the operating system is doing on behalf of the Memcache. And in particular, you're spending a lot of time pushing packets in and out of the network interface. And it turns out that the code paths to operate a networking stack are actually quite long. And so when we put this on a high-end server, we get very good performance. But in fact, we reveal some inefficiencies. Some of these really high-end components of the processor that are designed to do really well on a scientific application are actually buying me very little when I'm running through this giant, very I/O-intensive code path of the networking stack. And in particular, as I'll show you with a couple of results, we find that all of the investment that computer architects have made into fetching instructions really well, things like large instruction caches and very sophisticated branch predictors, actually do a really horrible job on this particular workload. And so the net result is that all of that energy that you're investing in those structures really is wasted. Similarly, these servers have giant caches to store sort of huge data sets for example, database workloads. But because there is so little locality in the actual data that's being served by the key value store, you're getting very little return on the substantial amount of chip area that's invested in these large caches. Now, if we go to the other end of the spectrum and try to make a super simple processor work, we'll find that relative to what I save in peak power or what I might be able to gain in energy efficiency, I'm simply giving too much performance up. When you stress something like an Intel Atom trying to run the networking stack at high performance, as load goes up, the processor simply falls over. It's unable to keep up. And in fact, you end up with drastically worse energy efficiency than the big iron machine simply because performance has dropped so much. And so sort of the stepping off point here is that both extremes of the commodity architecture space are really ill-suited for handling lots and lots of small network packets. And perhaps there's an opportunity to do something different. And so, the approach that we took here is to sort of go back to Computer Architecture 101, to the Hennessy and Patterson textbook, make the common case fast. And so the common case for the vast majority, though not all, Memcached workloads is that you spend most of your time doing gets. You're mostly reading keys out of the cache. So for example, Facebook reported that sort of averaged over a bunch of the different workloads, 30-to-1 ratio of gets to sets is typical for some of their uses of Memcached. So the idea with thin servers with smart pipes is to try to get all of the work of processing gets off of the processor and into a specialized pipeline. So let's simplify that problem as much as we can so that with a relatively simple piece of hardware, we can interact directly with the network and actually execute get requests without invoking a single instruction on the processor. So that means we're going to need to deal with the networking stack, packet decipher, generating responses, and also managing the actual data structure that allows us to locate values from keys. But at the same time, it would be quite difficult to implement the entire Memcached software entirely in hardware. And so we defer more complicated things, like, for example, managing memory and deciding exactly where to allocate objects, or managing the replacement policy in the cache so that we do something that's perhaps an approximation of least recently used. These things we defer to software, and hopefully we've taken enough load that now a much simpler processor can actually keep up with the demand. So this is sort of what we've demonstrated in sort of an FPGA-based prototype. And if you project what this would look like in a platform where you have an FPGA integrated with a processor, something like a Zinc, or maybe something with a little beefier processor than a Zinc, we project a performance per watt advantage of 6x over the high-end server and 16x over the first generation Atom that we measured here. And that's already sort of a win that's in the ballpark of worth considering, perhaps deploying several thousand of these things to replace a Memcached pool. So with that, I'll briefly give you some background on Memcached in case you've never seen it before. And then I'll take you through some of the insights we gained from this characterization study, and then just show you a couple of pictures, sort of block diagrams for what were the key decisions we made in this relatively simple offload engine for GET requests. And then I'll conclude. So, so I've sort of said some of this already, but a typical architecture for a web service is that you'll have some kind of stateless presentation layer or front end that's actually executing terminating the connection to the external user and running the web server code and so on. So in the case of Facebook, it's actually the entire Facebook application runs statelessly in these web servers. And you have a third layer down here, a database layer, some kind of storage layer, which is the ultimate durable store for all of the data that gets written or updated by web server requests. And if we simply had the web servers talk directly to the databases, we'd have an extremely expensive solution because the amount of code you need to run to make stuff durable and reliable and so on is quite large. And so we'd either need a heck of a lot of database servers, or perhaps we wouldn't even be able to keep up with the massive amount of throughput that all these web servers can generate. And so since most of our requests are reads, we can improve the overall cost effectiveness of the system by introducing these caching layers in between, where the Memcached can respond much faster, respond with much higher throughput per dollar. And most of our traffic will get served by these specialized Memcached pools for various applications. And only writes need to all be reflected all the way back to the database. And so the details on how you do this, of course, differ, and the real pictures are much more complicated. But this is the basic idea of why Memcached is a cost win for a lot of web services. And so what we want to understand is how can we design some kind of more peak power efficient or energy efficient system if really all it has to do is Memcached and doesn't ever have to run anything else. And really what we discovered in measuring these existing servers is that you get really poor performance for serving very small objects, which is a very common case out of these Memcaches. So I'm showing you two graphs here. The first graph over here, the horizontal axis on both graphs is object size. Okay? So what is the size of the thing that we're getting out of Memcached? The vertical axis here is throughput, so higher is better. And over on this part of the graph, you can see that we can basically hit theoretical throughput in practice, right? Basically, we're limited by the bandwidth of the network. There's really nothing else you can do. This is the best case scenario. We're sending data. Everything's wonderful. However, as the object size gets smaller and smaller, at some point, the actual achieved bandwidth on a real system falls drastically short of what you would project if you just took the data size and divided it by the serialization delay of writing it to the network. And what's going on here is that the CPU is no longer able to keep up to execute the networking code to get the packets out fast enough. It's simply falling short on the number of I/O operations per second that need to be executed to actually curate all of these packets. And so you see our CPU here, the single CPU that's pushing this traffic, is pegged at 100% for any object size that gets sort of close to that 64, 128, 256 byte limit. And so the CPU is the bottleneck, but why? What in God's name is it doing? So we basically took various, we wanted to understand what the hardware was doing, what the processor was doing, by doing load tests with sort of traffic that was designed to represent various Facebook-like use cases, and really ask what is the microarchitecture doing? What is the thing that's limiting instruction throughput? And also, what is this interaction with the NIC? What is going on, and how can we improve the interaction between the CPU and the NIC? And so we've looked at sort of two classes of processors, as I said before, and these things are very different. So the frequency is much higher in the server class part, which is the Xeon over here, has much more caching. It has a much more capable memory interface that's capable of higher bandwidth. And with both of these two servers, we've also tried a variety of different networking hardware to understand how much can a better I/O interface and a better network interface buy you, and how does that compare to, for example, the alternative of having a faster processor. So I've sort of already told you at the beginning the main results, but relative to the theoretical peak performance that you could get out of a Xeon or an Atom, these workloads use the microarchitecture very inefficiently. So the graph that I'm showing you here, the vertical axis is the number of clock cycles the average instruction takes to execute. So this is a graph where lower is better. And for the Xeon processor, in theory, if we were pushing the processor completely to the metal, running some kind of scientific application that has lots and lots of parallelism available, we could get well under 1 clock per instruction. We could do 4 or 5 instructions on average every single clock tick. And yet, as you can see here, we're a factor of 5 to 10 worse in terms of using the theoretical capability of the microarchitecture, and we're somewhere between a factor of 2 and 4 worse than the typical applications that people in the computer architecture community study, things like scientific computing applications, which tend to use the microarchitecture quite well. So we're very far away from what theoretically could be going on. So why are instructions taking 2 to 8 cycles? Where is all this time being lost? And to our surprise, what we discovered when we actually looked at the various stall sources is that the largest bottleneck, and the one that stood out as most unexpected, was instruction cache performance. That is the structures in the processor that are trying to accelerate instruction supply. Instruction translation, instruction cache, and also branch prediction. And we're surprised at this because the code is so small. What in God's name is Memcached doing? And the reality is that it's the kernel and the massive bloat of the TCP/IP stack and other aspects, so things like locking and memory management, that put tremendous pressure on these hardware structures. And so we end up seeing these structures overwhelmed when we compare them to, again, the kind of desktop and engineering applications that the architecture community is so fond of having bar graphs of in all of our papers. So this is sort of something that we'd like to address, and the way to do it is to get rid of some of these instructions. Let's not run through these giant code paths. Let's try to move some of these very long code paths to the accelerator in the common case. The second thing that we did in this characterization study was take a look at how much better can we make things if we use a smarter network interface. If we use a better NIC, a more capable NIC, NICs with features like interrupt coalescing or receiver-side scaling, where the NIC will actually take pains to steer TCP flows to particular processors or to reduce the frequency with which they send interrupts to the processors. And so we started sort of with the cheapest NIC you could find, some commodity garbage that probably came from eBay or something. And then we sort of spent money on what's sort of the best state-of-the-art NIC we could buy. And we also asked the question, is it bandwidth or is it really these interface features of the network interface that improve performance? And so in some cases, for workloads where messages are large, like in this image preview and wiki serving application, bandwidth, in fact, helps a lot. So these 2 rightmost bars here, we went from a 1 gigabit to a 10 gigabit Ethernet card. And unsurprisingly, performance goes up drastically if you're really limited by the serialization delay of the link. However, what again was somewhat of a surprise to us initially, although is obvious in retrospect, is that for very small objects, in particular these 2 workloads over here, microblogging and our simple fixed object size workload, they're super sensitive to how efficiently the NIC interacts with the CPU and how often it interrupts the CPU. And simply taking fewer trips through the software stack leads to somewhere between factor of 2 and factor of 3 performance increases. So what we took away from this is tight integration with the network and trying to get the processor out of that interaction path is a potential win. So with these observations then, we proposed this idea, thin servers with smart pipes. So by making the pipes smarter, by being able to talk directly to the network without software intervention, perhaps we can reduce the load on the processor to the point where a much thinner processor is able to keep up with the remaining work. So we take advantage of trying to get rid of these frequent network interface interactions, taking advantage of the fact that GET requests dominate. So as long as we can get the GETs out of the way, there isn't all that much left. And we propose this SoC architecture that takes the low-power core and integrates this accelerator pipeline for processing GET requests. So I'll just show you a couple of quick pictures. These are sort of block diagram cartoons of how this thing works, but I'll try to highlight very briefly some of what we thought are sort of the important reusable ideas that might apply to some other kind of accelerator. So this is just sort of a system block diagram. There's nothing super surprising here. This is sort of any SoC might look something like this. But a key decision here is that you see we have this Memcached accelerator. This is the custom piece of hardware that we're sticking on the side and modeling in our FPGA. Speak directly to the NIC, and I'll show you how that interaction works. And another key design decision is that we have a shared system MMU that allows the Memcached accelerator to translate main memory and actually access main memory in concert with the software that's executing on the CPU. So basically, virtual memory is shared between the accelerator and the CPU. And this is, again, that's not rocket science. This is something that you can do with an IO MMU architecture that various vendors have available today. So if we zoom into that Memcached accelerator block and try to understand sort of that arrow of how the NIC talks to the accelerator. So this diagram zooms in a little bit. The top part of this diagram is sort of a couple of blocks that you have in a fairly conventional network interface. And the bottom half is the accelerator, the new widgets that we've added on the side. And so over here, we have the interface to the actual network. So you have your physical layer and sort of the first levels of error checking and so on. And in a conventional NIC, there's this component called the flow affinitizer, which is the thing that's deciding which CPU should I send the interrupt to for this particular flow, exactly which receive queue should the packet get directed to, with the objective of trying to get sort of the same flows to go to the same CPUs over and over again to improve locality. So this is the point where we hook into the system, and we have the flow affinitizer identify packets that are Memcached GET requests, and there we used a cheap trick. We send the GET requests over UDP, and so all UDP packets are destined for our accelerator. All TCP packets go through the normal processing pipeline. And we dump them down to our accelerator over here. A UDP offload engine handles the actual UDP protocol, which is fairly simple because you don't have to remember a lot of stuff like you do with more complicated network protocols. We go through a packet decipher layer, which figures out, is this a well-formed GET request, and what is the key, and what is the fingerprint of the key, and what am I looking for? We go through a hardware hash lookup step, which I'll show you one more slide on, which actually determines whether the key is present and finds the value in memory. And then we do DMA to assemble the response packet, and then shove that back into the transmit buffer directly in the NIC, all without any interaction from the processor, okay, for the common case. So let me briefly zoom in on sort of how does this hash lookup work, and what is the split in responsibility between software and hardware. So the idea, again, is simply to make the common case fast. And so we want a very simple hardware hash table that's very easy to implement. However, we want to avoid synchronization overheads between software and hardware. And the software is going to be responsible for actually inserting new objects into the key value store. So the hardware uses some ideas sort of that come from things like cuckoo hash tables, where you can get very, very good load factor, very high storage density on a hash table by actually having multiple alternative locations that a key could hash. And in addition to having sort of 4 locations that will look up in parallel, because this itself can still fill up, we have sort of a associative lookup memory that handles overflows beyond that. So the hardware is basically going to look in 4 spots and look in its overflow buffer. And if it can't find the object there, well, then it must not be in the key value store. Software is responsible for dealing with the memory allocation, of actually efficiently packing all of these objects in memory and maintaining LRU and so on. And so here we have a fairly standard memory allocator. It's a slab allocator. And the key idea is that software does not directly manipulate the hash table data structure that's actually used in lookups. Instead, to avoid any need for synchronization, the software actually delegates the responsibility of maintaining the hash table to the hardware. It'll insert requests to change, to insert keys and remove keys from the hash table into the hardware pipeline. And so the hash table is, in fact, touched only by hardware. So I think the takeaway from this is not the details of this particular design. This is just, we had a relatively simple problem and we solved it with relatively straightforward mechanisms. I think the principle to take away is to think about this hardware versus software complexity partitioning, and to think about issues like synchronization between the hardware accelerator and the software, to find a very simple interface. And here the interface is extremely simple. The software simply asks the hardware to make some very small changes to the hash table as needed. So our evaluation here is a little bit of a sort of a Frankenstein evaluation, since we actually don't have a full implementation of the entire system. But we have measured the accelerator component, the actual thing serving GET requests via UDP. And from there, you'll have to take some of the power numbers with a little bit of a grain of salt, but they're projected based on looking at similar SoC systems and figuring out what would the processor be, how much power would the actual accelerator component use, how much power would the networking use. The numbers on the Xeon and the Atom are actual, real, measured power and performance numbers. But so through the lens of the limitations of sort of spreadsheet analysis of power, we still are well over an order of magnitude more efficient in terms of operations per watt or performance per watt. And so, an order of magnitude, even with sort of the approximations here, even if we give some of that back, we're still doing quite a bit better, and yet still maintaining a quite respectable peak performance from one particular Memcached server. relative to what the real servers can accomplish. So let me just briefly conclude. So as I've sort of said, Memcached, there's a lot of Memcached servers in the world. It is probably worth thinking about how to make it more efficient. Perhaps not. It's unclear that a hardware accelerator is the way to go, but there are enough of these things that if you can find a way to make them single-digit % more efficient, you're still saving lots and lots of money for some big companies. And we discovered that frequent network interaction really was a key performance bottleneck. And so finding a way to get the common case software path out of the way was a good way to improve performance. And so we've demonstrated this hardware approach to get gets to execute completely in hardware. But more broadly, from here, one of the things that I've taken away from this is that you really want to do compute-intensive stuff in accelerators. And this is not a particularly compute-intensive operation. Now, the TCP/IP stack, I guess, has a fair bit of code, and so there was a lot of value in getting it out of the way. But really, looking forward, I don't think I would pick Memcached again as the workload to focus on. I think I'm much more excited now about accelerators for media-intensive processing. You have lots of bits. You have to do some kind of streaming operation over lots and lots of bits. Or things like machine learning and inference that are really becoming increasingly important, right? Doing these massive models, like, for example, you're going to hear about in the next talk, where there's lots of number crunching that needs to go on. That number crunching is drastically more efficient when you drop down a custom piece of hardware than when you implement it with something like a really energy-intensive out-of-order processor. And so, with that, I think I'll take any questions you have, and hopefully that's a good setup for what Adrian's going to tell you next on how you can really do machine inference very well with FPGA acceleration.
Let's thank our speaker. So we have time for questions, just a few minutes, but please wait for the mic.
Jim.
So, Tom, if the TCP/IP stack is the problem, isn't the solution to fix the TCP/IP stack rather than build this special purpose piece of hardware to work around it?
Yeah, so I agree the TCP/IP stack definitely needs fixing. It has gotten better. So these measurements were done a couple years ago, and I think a lot of effort has been invested. But you can't do better than making it go to zero. So here we've sort of taken it completely out of the picture. And I mean,
right, but the work that you allude to has basically reduced the overhead of TCP/IP. So it's at least for Memcached, it's not on the critical path anymore, and you can't do better because you can saturate the 10 gig ETH.
Yeah, so I think that'll help a lot with the sort of the instruction cache issues we're seeing, and that would no longer be the bottleneck. However, it's still 97% of your traffic is these GET requests. And the question that remains is, even if I make TCP/IP faster, can a wimpier core keep up executing the Memcached software and executing TCP/IP, or will it hit some other bottleneck? And if it's still hitting another bottleneck, then I can't go down to this really cheap core that I'd like to be able to use. So by moving this common case completely into hardware, now I'm left with much less work to be done on the general purpose processor. And now a wimpier processor will be able to keep up. So the question is sort of, do my software optimizations get me to the point where I can get away with a processor as wimpy as I'd like or not? And I don't have an answer to that question. I mean, we'd have to go back and measure again with the latest Memcached and the latest changes in the Linux kernel for TCP/IP to figure out just how wimpy can I get and still keep up.
So let's take just one more question over there.
I had 2 questions.
Okay.
Quick follow-on to the last one, just for clarification. I had the same question about TCP, and I thought a lot of people use actually UDP for gets, and it seemed like you in fact used UDP for gets. So I was a little confused what your analysis of then showing TCP locking was.
So we did measure the performance change from just switching to TCP to UDP, and it's 10%. You get 10% better.
Okay.
So I guess when I say TCP stack, I should probably more generically say the networking parts of the kernel.
So my real question was, I've seen also some other work who basically try to replace the get path with RDMA. And so I'm wondering if you could, it sounded like kind of you reconstructed a whole RDMA thing. So I was wondering if you could kind of compare these two things.
Yeah, so I mean, I think, so there's, I think, some work out of Ohio that demonstrates RDMA-based Memcached, and you get drastic improvements. And so I think that's actually a very exciting direction to go. I think.
Given RDMA is kind of mature, why not, I mean, why do you go this direction rather than just asking about RDMA?
It's quite expensive. I think that's the one downside of the networking hardware you require for RDMA relative to sort of. Okay, but yeah, I think that makes sense.
All right, let's thank the speaker again. Okay, so our last speaker of this session is Adrian Caulfield. Adrian joined Microsoft Research in July 2013, focusing on using reconfigurable computing to accelerate large-scale data center workloads. He holds a BA in CS from University of Washington, Seattle, an MS in CS, and a PhD in computer engineering from University of California, San Diego. His dissertation focused on the development and optimization of solid-state disks targeting emerging memory technologies such as phase change memory and spin-torque transfer MRAMs. He also worked extensively with flash memory during his time at UCSD.
Great, thank you.
Yours.
So I'd like to talk to you today about reconfigurable fabric that we've been building here at Microsoft for accelerating large-scale data center services. This is work that's been done by a large number of us here at Microsoft, but basically led by Doug Berger and Derek Chu. And you can imagine at a company like Microsoft, we run a large number of services in the cloud. We're very concerned about how efficient these data centers are. And it's one of the key factors that we consider when we're designing equipment for the data center. And so over the last couple of decades, we've been able to sort of rely on improving processor technologies to increase the efficiency of our data centers. That's sort of tapering off, and we have to start looking at other ways of finding efficiencies for our data center services. And this is a graph that shows up fairly commonly in architecture conferences, but basically what it's showing is as we move from general purpose processors, shown on the left, to sort of more dedicated hardware with ASICs, like Martha talked about in her introduction, we can get significant performance improvements from 10x to 100x or even more. And so the key point here is that we can increase our data center efficiency by increasing hardware specialization. But at a company like Microsoft, we have a couple of additional challenges that we have to deal with in the data center. When you run services at these scales, we push updates out to our software regularly. Software changes at least monthly, if not more. The machines that we buy last several years, and they're purchased on a rolling basis, so we can have 6 or more generations of machines active in the data center at the same time. And a lot of these machines are repurposed halfway through their life cycle. So they might start out running Bing code, but then they end up running Skype or some other service that Microsoft cares about. And because we have so many machines, it's really hard to go out there and do maintenance on these machines. We can't just drop in additional hardware if we decide we want a different ASIC in the hardware. So homogeneity is highly desirable in our data centers. So we're sort of left with a paradox, right? We want this specialization that we can get by building ASICs and specializing our hardware, but we also want the homogeneity so that we can run all of our services on any of these machines that we buy. So if we go back to this graph, the right side is ASICs, left side is general purpose processors, and in the middle, we think there's space for a number of FPGA-based accelerators, and these trade off some of the efficiency, but at the cost of, or with the benefit of allowing us to actually adapt the hardware that we're deploying and change it as software services change. So if we look at an example, if we have a server that gets purchased by Bing, this sort of gives you an idea of the spectrum of Xeon CPUs give us a lot of flexibility. Any software that we push out, we can change as the software changes. On the right side, we have very specialized hardware like a network interface. This is something, we're willing to put NICs in all of our machines because obviously we need network connectivity. But in the middle, there's space for putting accelerators in these servers. So we have 2 options, right? We can build a search accelerator using an FPGA. Gives us reasonably good efficiency and flexibility, or we can build it on an ASIC. But if Bing decides later to change their algorithms a little, what happens? Well, that ASIC becomes either totally or partly redundant. Now it's just sitting in our server. It's wasting power. And it's holding back the software from making the changes that it really needs to. And if later on we even roll a server over to a different service, that ASIC is definitely wasting power now. It's not actually doing anything for this new service. But if we had an FPGA in there, we could actually push out an entirely different accelerator and make use of that resource in the servers. So we believe that there's a lot of space here to basically build accelerators on FPGAs to give us some benefits. So when we started this project, we had sort of two simple design requirements. The first is, let's build some specialized hardware using a nice general purpose FPGA fabric. But also, let's keep our servers homogeneous. It turns out, if we're throwing stuff into our data centers, we actually have a few extra requirements that get tacked on. The first is, don't add too much cost to the servers. We have to stay under about 30% of the cost of the blades. The second is, we can't add significant power draw to the servers. Our data centers are provisioned for a certain amount of power per blade. We're given about 25 watts to power whatever accelerators we want to put in there. And then finally, obviously don't break anything. We have to work with the existing servers. We're not redesigning the hardware around this new accelerator. We can't modify the networks. We can't increase the hardware failure rate. And so really, it's these very simple constraints in the middle, but there's a lot of other stuff that gets piled on top of it. So the data center servers that Microsoft uses are these open compute blades. We released the designs publicly. Basically, they're 1U half-wide servers. I have an example of one up here that you're welcome to come and check out later. But basically, there's enough space at the back of this blade for a tiny little accelerator card. And this is a PCIe Gen 3 device. And we basically squeezed an FPGA into that spot. And so these blades have Xeon processors, a healthy amount of DRAM, hard drives, and SSDs. And one of the nice things is all the cabling is attached to a backplane at the back of the server. So if you do have to do maintenance, you don't actually have to uncable everything and plug it all back together. And so the FPGA sits at the back. And another constraint that we ended up with here is we're actually sitting at the back of the server after all the air has been heated up by the hard drives and the CPUs. And so basically, by the time it gets to us, it's really not very cold anymore. So we have to be very careful about how we can properly cool these FPGAs and these devices. It's just something you don't necessarily think about when you're initially designing it. So we're using a fairly high-end Stratix 5 FPGA. It's got about 173,000 ALMs. As I said, it's PCIe Gen 3. There's 8 gigs of DRAM on the board itself. And it occupies a PCIe slot and draws its power from there. And one of the design decisions we made with this device is to actually build a dedicated Taurus network to connect all of these FPGAs together. And one of the motivations for that is that we want these homogeneous servers. We don't want to have to build a box, put a bunch of FPGAs in it, and then try and send requests over to that dedicated device from each of the servers. So if we put one in each FPGA, about 48 of those in a half rack, and then we can connect all of these with a 6x8 Taurus, and that gives us a very low latency network to talk between FPGAs and allows us to scale out services that might need more resources than just one FPGA. So if we look at how a fabric of FPGAs might interface, and give you some more motivation for why we need a dedicated network, if we take a bunch of CPUs and attach a bunch of FPGAs via PCI Express, if we have a service that maps across 4 of these FPGAs, we actually, if we want to talk between them, we end up going up and down through this software stack. And as Thomas just told us, going through the CPU and that networking stack is actually pretty expensive. So if we change this and actually build a dedicated network between the FPGAs, we can reduce that latency down to just a couple hundred nanoseconds per hop. And it makes it much easier to map our pipeline on top of that. And we can also fit a lot of other data center services onto this fabric if we want to. And depending on what resources they require, they can use different numbers of FPGAs. So another challenge with using FPGAs at a company like Microsoft is how do we make these devices actually approachable and make development for them slightly easier? And one of the ways we've done this is to essentially include all of the I/O and the management tasks into what we call a shell. And then we isolate all of the application logic into a role. And the role has a very simple FIFO interface for moving data into and out of it. And that allows us to direct traffic to the other FPGAs and the Taurus, as well as to the PCI Express core to get to the host or to the DRAM controllers. And with these applications, we picked a fairly easy one to start with, which is actually accelerating Bing ranking. Maybe just a little sarcasm there. But basically, if we look closer at Bing ranking, it's actually divided up into 2 key components. The first is what we call selection as a service. And this is the part of the service that actually takes your query and our large document index and selects a number of those documents to be ranked and to present a final score. So these are basically documents that contain all of your keywords that sort of match what the intent of your query was. And those get sent over to the ranking half of the pipeline. And these are the ranking side essentially computes a score for each document that says this page is this relevant to your query. And then you take those final scores, you sort them, and that's how you get the 10 links that end up on your homepage or on your Bing search page. And so we actually looked at accelerating this whole ranking half of the pipeline on FPGAs. And so it's broken down into 3 distinct stages. The first is called feature extraction. And in feature extraction, we'll take your query and a copy of the page and calculate a number of what we call dynamic features about this page. So for example, how many times does the first query word appear on this page? In this case, FPGA shows up 7 times. Similarly, second query word, we can do the same thing. Or how many times do the pair of words show up next to each other on the page? In all, there's about 4,000 of these dynamic features that we're calculating, depending on the query and the page and things like that. And all of those features get sent from the feature extraction stage onto the freeform expression calculation. And this essentially allows us to take arbitrary computations based on these dynamic values. And these are all sort of complex floating point math operations that we're doing. So we can calculate, we plug all these variables in, we end up with a number for each of these freeform expressions. And those get sent down into a machine learning scoring stage at the end of the pipeline, which I actually can't talk about today. But if we look a little bit closer at sort of how these are implemented, we can see why we're getting a significant win on the FPGA based versus what we can do on the CPU. So for feature extraction, I said there's roughly 4,000 of these features. They're spread over about 200 different families of features, and those are implemented in about 54 different state machines inside the FPGA. So we take the streaming document coming in, and we feed it into all of these state machines, and we process them in parallel. And that allows us to cut down the processing time to about 4 microseconds from roughly 600 on the software side. So this is obviously a pretty big win. And then all of these results get forwarded over to the freeform expressions. And these are implemented as a number of soft-core processors on the FPGAs. So there's actually about 4 hardware threads per core. They implement log, divide, and a number of floating point operations. And 6 of these cores all share a complex unit, and we do some scheduling to basically make sure they can all share that safely. And on each FPGA, we can fit about 10 of these clusters, or about 240 hardware threads. So there's a lot of parallelism that we're getting in the FPGA that just wasn't there or wasn't available to get on the CPUs. So if we take all these components and we stick them together into a pipeline, basically we have 1 feature extraction FPGA, 3 of the FFE blocks, and then the machine learning scoring at the end. And you'll notice that we have an 8th FPGA at the bottom that's actually a spare. And we use this for fault tolerance, which I'll talk about in a minute. But to actually accelerate this ranking pipeline, we take documents from all of the servers hosting these FPGAs and allow them to inject at any point in the pipeline. And the request will get injected, passed up to the top of the pipeline, and then moved all the way down through the pipeline. The final score is produced and then sent back to the server that injected it. And these all happen in parallel. And basically, because the servers just see the connection to the fabric, they don't have to be aware of what all the other FPGAs are doing in the pipeline. All of that routing is taken care of on our Taurus network. So like I said, there's some challenges to basically making this work at scale in a distributed manner. And basically, with the pipeline formations like this, one of the big things we have to be able to do is map around FPGAs that have failed. So if FPGA 2 suddenly goes out, maybe its power supply fails or something like that, we actually need to be able to shift this pipeline around that FPGA, basically route around it in the Taurus to be able to deal with that fault tolerance. There are also a number of general issues that we deal with FPGA fabrics in the data center. Essentially, we have this problem where if a PCIe device goes away while you're using it on the bus, we need to be able to handle that robustly and basically reconfigure the FPGAs. We have to deal with ion strikes if our configuration bits in the FPGA get scrambled due to random particle strikes. We have to use SEU scrubbing, single event upset scrubbing to deal with that. And there's also an integration time when these things are first delivered. There's a huge number of problems with making sure they're actually wired up correctly and doing all the checks that are required there. So we've actually deployed 1,600 of these Catapult boards in a production data center, and we've run Bing traffic through these devices. So this is pretty cool. And this graph gives you an idea of the performance benefits that FPGA accelerators can get in the data center. So this is looking at the 95th percentile query latency versus throughput. So the x-axis is latency normalized, and the queries per second on the y-axis is normalized. The blue line represents our software-only performance running Bing's ranker. And the orange line represents the performance with software with the additional FPGA accelerator. And so if you look at the 0.11 on the software line, if we decide that we want to maintain sort of constant latency, we can actually double the throughput in terms of number of documents per second that we can handle by adding the FPGA. Or we could decide to keep the same throughput and basically reduce latency by about 29%. And we've managed to do all of this while maintaining all of those constraints that we set out at the beginning, which is less than 30% cost, less than 25 watts of extra power. We've seen basically no hardware failures in terms of like board failures and things like that since we've deployed these. So we're pretty confident in the robustness of the solution and our ability to scale this up. So in conclusion here, I'd just like to say, we think that hardware specialization is a very good way of increasing efficiency in the data centers. It may be the way to increase efficiency in the data center. And we've found that an FPGA fabric is really a good way of offering a flexible, elastic pool of resources to accelerate services. We've shown that with Bing ranking, we can sort of reduce the number of machines that we would need to implement data center services by half, while maintaining lower variance in terms of latency, offering lower latencies. And we've proven the scalability and resilience of these devices. And there's obviously huge potential for future applications to be accelerated with these devices. But the real question that we get asked a lot is, so when is an FPGA going to start handling my Bing web search? And the answer is, this isn't a toy. Bing has made a production commitment to take these devices into production. So sort of early next year, we'll actually have FPGAs handling a fair share of our Bing web searches. So the final takeaway here is, I think we're moving from a model where we have programmable software running on fixed hardware devices to something more like a programmable software and programmable hardware deployed in our data centers. So this is pretty exciting. Obviously, this is work done by a lot of people. A few of them in the picture there. There's a bunch that aren't in the picture. And with that, I'd be happy to take any questions.
Let's thank the speaker. I don't remember who came up first, so why don't we just go in that order?
Very nice talk, thank you. Do you have any number about utilization of FPGA? Like, are they always running busy, or they're like 50% idle, time idle?
So, I mean, it depends a lot on the workload. So some of our stages are actually faster than others. But sort of in terms of logic utilization, we're pretty much using all of the resources there.
Right, but the FPGA being busy all the time?
Yeah.
Is that busy all the time, or still like?
So
right now, basically, you dedicate FPGA to one server, right? So I asked the question to see if there's any potential for sharing one FPGA among multiple servers. So that's why I asked this question.
Sure. I think the answer to that is, at the moment, switching between services is fairly expensive. And because we're actually using all the resources for that one service, it's fairly challenging to sort of time share the FPGAs in that sense. At larger timescales, certainly I think there's opportunity, right? Like, web search traffic is very cyclical. During the day, there's a lot more searching than happens at night, so you could reduce the number of FPGAs that are running that service and run other workloads. But sort of when these services are running, they're fairly well occupied, right?
Thanks.
So let's do the two back there. Those were up first.
Thank you very much. I wanted to ask you about the software versus FPGA firmware configuration, development, debugging, stabilizing. I mean, we have a lot of experience of turning software very quickly. And when you move to the FPGA, that makes it more complicated. I wonder if you could speak to how you work that into your software pipeline.
Sure. So certainly at the moment, the hardware development is a little bit more challenging. You know, we're definitely pushing for sort of higher level synthesis tools. You know, I talked about those 50 state machines that sort of implement the various features. In this implementation, those were all sort of written by hand and sort of verified independently. But I think there's a lot of room there for taking, you know, they're actually relatively simple kernels that we're implementing. So there is a lot of potential there for developing sort of higher level synthesis tools that could tackle a lot of that. But certainly at the moment, the hardware development cycle takes a little bit longer. But you know, it's sort of one of the prices that you're paying for the increased efficiency that we can get.
Back there was one question.
I think you mentioned the freeform expression was pretty FPU dominated.
Yep.
And FPGAs generally aren't known for doing a good job with floating point operations. So I guess I'm wondering, are there other substrates that you would prefer to use for that part of the pipeline, or what are your thoughts on that?
So, you know, I will say FPGAs are generally moving in the direction of supporting more floating point. So I think, you know, that's certainly true at the moment. But as we go forward, I think we're going to see sort of more floating point support. The other thing is, when we did this, we were basically given the requirement that our scores would match exactly with the software implementation. And there's obviously a lot of room here for taking floating point and turning it into fixed point and sort of optimizing there. And you know, as we move into production with this, that's going to obviously be something we're looking at.
There's a question up here. And then I think we'll take the last one back there.
I'm interested in a apples-to-apples comparison when it comes to investment in hardware, because clearly you invest much more in hardware. So you could have taken the same investment and buy larger servers, many more processors. So the question is, if you look at it from this angle, and it's not clear to me what would be a proper apples-to-apples comparison, so that's part of my question. But if you look at it from this angle, are you really getting ahead, and if yes, by how much?
Sure. So, you know, the question is basically, if we just took the money and bought more servers, would we end up better off overall? And I think the answer to that is that, you know, we can get more out of the FPGAs for certain computations than the CPUs would be able to achieve, sort of for the same power and cost numbers. I think the point is you have to balance sort of how much compute you're putting on GPU or on CPUs versus, you know, what you're putting on the FPGAs. And you know, I don't know exactly what the right apples-to-apples comparison is, but I think that there's definitely benefit to spending some of the money on different types of computation than just general-purpose CPUs. Does that make sense?
I think there's one last question, and we'll conclude.
Right, thanks for the talk. You had made some sort of parenthetical comment at the beginning of your talk about how a GPU wouldn't fit into that form factor, wouldn't fit into that power budget. Was that ever a real consideration where you were looking at GPUs running or supporting search in some way?
So I don't actually know if the group looked at search on GPUs. It's certainly a discussion that's been happening you know, around Microsoft Research and things like that. Is like, you know, what's the right accelerator technology? But you know, there's computation that FPGAs can do that GPUs can't, and certainly with FPGAs moving towards more floating point computations, there's sort of, you know, the benefits of doing GPU versus FPGA are sort of eroding a little bit in terms of that computation. So I think, you know, I'm not sure that we did look explicitly at ranking on GPUs, but We did, okay. Jim was here before I was, so. But yeah.
Okay, so let's give applause again for our speaker.